Hello guys, this is Trockers. Thank you so much for tuning in. Okay, we have a problem on numerical methods from ZIMSEC, June 2017, paper 1. All right, the first part, by sketching the graphs of y equal to natural log of x and y equal to x over x minus 1 on the same axis, show that the equation natural log of x equal to x over x minus 1 has exactly two real roots. Show by calculation that one of the roots found in part A lies between 0.3 and 0.45. Then taking 0.45 as the first approximation to the root, use the Newton-Raphson method twice to find the root correct to 4 decimal places. All right, so guys, we can make some annotations here so that it makes sense. Right, we want to sketch. So by sketching, guys, you're just showing key points. And usually the key points are the intercepts, the coordinates of the intercepts, as well as if we have meeting points for those graphs, if we have points of intersection as well. Then what else do we need here? We have this graph here. So it's a graph of x over x minus 1. We don't know that graph offhand unless we think of a parent function which we can derive from here. So obviously, when we have this graph of 1 over x, we can play around with the transformations to get to this part, right? And we want to show that it has exactly two real roots. So in order for us to show that it has two real roots, there must be 2 points of intersection, right? Okay, then moving on to part B. So on part B, we are using the intermediate value theorem, which is the sign change method. So in this case, into our function, we plug in 0.3. If we get a positive, then when we plug in 0.5, we get a negative. It means the graph is continuous between that and we have a solution. So what it means is that when you have your axis here, right, then you sketch from 0.3 because that's a continuous graph. So from 0.3, you get a positive solution. Then from 0.5, you get a negative. But remember what I'm saying, the graph is continuous. So somewhere, somehow, it passes through the x-axis, hence we have a solution there. Right. Then on part B, we are just going to use the Newton-Raphson method twice. It means we are going to use it 2 times, and that's it. Right. Whatever the answer we have, we are supposed to estimate it to 4 decimal places. Okay. So with that being said, guys, let's go ahead and get started. All right. So we need our whiteboard here. Okay. So these are the two functions these are the 2 functions that I need to graph. Okay, the first one is y equal to natural log of x, and another one is y equal to x over x minus 1. So quickly, I can start with the graph of y equal to x over. So for x over x minus 1, we can use algebraic manipulation, or you can divide. So here you rewrite this as x minus 1, but since this was x, you have to add 1 over x minus 1, such that we have x minus 1 over x minus 1 plus 1 over x minus 1, which is just 1 plus 1 over x minus 1. Now it's easier to identify the transformations. So always when you are doing our transformations, remember this is our parent function, which is 1 over x. Everything else in black, these are transformations. So let's start. When we start, we know that the graph of 1 over x here, it has 2 segments. It's hyperbolic in nature. One is in the first part is in first quadrant, the other one is in third quadrant, right? The key point there is the origin, which is 0, 0. Then if it's minus 1, we are shifting 1 unit to the left, right? We are shifting 1 unit to the left. So what happens is that your graph will be like this. Whatever was happening at the origin will now take place at negative 1. So your graph will be like that, right? So remember, it's now, this was 1 over x, and this is now 1 over x minus 1. So when x is like this, is equal to y. So when x is, when y is 0, right? Do I want, do I need 1? Here, when x is 0, y is negative 1. No, is it y negative 1? Because what happened is that I have this function here, 1 over x minus 1, and I'm shifting 1 unit. No, I'm sorry, I'm supposed to shift 1 unit to the right, not to the left. I'm supposed to shift 1 unit to the right here. Okay, I'm moving 1 unit to the right. So whatever was happening there will now take place at this point, such that we have this, we have that. So it's now 1 over x minus 1. So y will be negative 1. Remember, when x is what? When x is 0, it's 1 over negative 1, right? Okay. I want you to see this. Then the other one is now plus 1. So what happens is that it's now a vertical shift. So the graph is going to shift. Whatever was happening at 0, 0 will now take place at 1, right? But the horizontal asymptote will not change, right? Meaning to say our graph will now be like that, and will now be like that. No, not like that. Okay, so here, remember this was negative 1. If I move 1 unit up, whatever was happening at negative 1 will now take place at 1 here. So your graph will be like that, right? Okay, so I think these are the key points here. You have your 1 up, you have that, and you have that. So now I'll go ahead and sketch this on one function, because we are supposed to show all the graphs on what? On one on the same axis here. Meaning to say I have this. So what I want is this and that, right? Or okay, let me do it this way. Okay, let me pull up the graph. Okay, so this is what I want. Okay. All right, that's my y-axis, that's my x. Remember, I have my 1 here. Right, that's my 1. Then I have my 1 there. That's my 1. Then that's the origin. So the graph was like this, right? And another graph was like that. So this is the graph of what? Y equal to, that's the first part, which is the graph of, this one here is the graph of y equal to x over x minus 1. The key point there is 0, 0 and my asymptotes, right? Then another one is y equal to natural log of x. So we know that, let me draw this in red. So for natural log of x, this was 1. Remember, the graph of ln is 1 is our x-intercept, and 0, y equal to 0 is our horizontal vertical asymptote. Okay, so now this is the graph of y equal to natural log of x. And as you can see now, you can indicate by showing the coordinates. So you can now give your conclusion, because according to this question, we are supposed to show that it has exactly 2 real roots. So you can just say, since these two graphs, since these two graphs intersect twice, therefore they are 2 roots. There are 2 points of intersection. Then we are done with the first part of what? Of the question. Right. So now let's move on to the second part of the question, which is question B. All right. So moving to question B here. All right. Part B of the question. Part B of the question is saying, show by calculation that one of the roots. So we had ln x equal to x over x minus 1. So we can rewrite this as natural log of x minus x over x minus 1. Now we want to calculate f of 0.3, meaning to say we are going to plug in 0.3 here. Then we are going to plug in 0.45. Whatever we get. Okay, so let's quickly do this. We have natural log, so that's natural log of 0.3, right? Minus 0.3 divided by 0.3 minus 1. So I'm getting negative 0.7754. Then let's do the same. Natural log of 0.45, right? Minus 0.45 divided by 0.45 minus 1, right? I'm getting 0.0197. This was negative, this is positive. So you write, since there is a change of sign, therefore there is a root between 0.3 and 0.45. Right. Just because there is a change of sign, remember I said this is called the intermediate value theorem, which we have used here. And you can actually check from this graph, guys. Remember, this is 1, this is 0. So obviously between 0.3 and 0.45, there is a root. This is one of the roots that we are talking about. All right, so now we are done with the first second part. Now let's move on to the last part, which is the Newton-Raphson. So for the Newton-Raphson, guys, you need to be careful. Okay, let me rewrite this as we have natural log of x is equal to x over x minus 1. So I want to write it in a way which is easier for us to differentiate, right? So if I multiply this, I cross multiply that, right? So that my function will be it will be x natural log of x here minus natural log of x minus x, right? This one is easy. Then from there I can just differentiate. So here we use product rule. It's u then dv, right? 1 over x u dv plus v du, so plus ln x, right, minus here 1 over x minus 1, right, which is just so this is 1 plus natural log of x minus 1 over x minus 1, which is just the natural log of x minus 1 over x, right? It's much easier here to work with. So remember, our function is equal to x natural log of x minus natural log of x minus x. Then our first derivative is natural log of x minus 1 over x, right? So now let's go ahead and apply the Newton-Raphson method twice. So remember the formula for Newton-Raphson method, it's xn plus 1 is equal to xn minus function of xn, right, over the first derivative at xn. Okay, so we want to find our xn, our x. We are given that x1 is 0.45 because that's our first approximation. Then to get x2, so you can write this statement, that's where you can write in full. Then the second one, you don't need to do that, is equal to x1 plus 1, which is equals to x1 minus f of x1 over first derivative of x1, right, which is equal to so your x1 here, okay, so your x1 is 0.45, so is 0.45 minus, all right, let me bring this down a little bit, okay, 0.45 natural log 0.45 minus natural log 0.45 minus 0.45, right, over, then it's natural log of 0.45 minus 1 over 0.45, right? So what I normally do when I use the calculator, right, let me try to come closer here. So when I use the calculator, this is what I do. I input the given, so I'll input 0.45, right? So when I say 0.45 here, it's now stored in the calculator. So instead of writing 0.45, you're going to write this structure as, so here you just say answer, then minus here, right? Then you put your fraction. So on top of the fraction, you are going to say answer ln answer, so it's answer ln answer, right? Minus natural log of answer, right? Minus answer over, then the denominator is natural log of answer, right? You close this, minus 1 over answer, right? So when I set it up like that, you only press it once. So when you press once, you're going to get 0.446. So you just write your answer as 0.4464178. Let me write it in full. Then to get x3, I'm going to say it's x2 plus 1. So it means I'm going to use whatever. So instead of, re-entering those values, you just press once the equal sign. So when you press once, it's now using the previous answer. So your answer is now 0.446432978. So therefore, the solution is 0.4464 decimal places. Right, then we are done. So remember, from the question, they say use the Newton-Raphson methods twice, right, to find what? To estimate the solution correct to 4 decimal places. So guys, this is what we did, right? Remember, this question is 3 parts. The first part here, was to sketch. So we sketched this graph. Obviously, I take note of transformations. You also need to know your parent functions graphs, right? Then from there, so when I say parent function graphs, these are the graphs in their simplest form. So you should know, as an A-level student, you should know the graph of x squared. You should know, which is this one, the graph of x cubed. You should just know it offhand, right? Which is like this. You should know the graph of absolute function. You should know the graph of 1 over x, the graph of exponential function, which passes through 1. You should know the graph of natural log, right? What else do you need to know here? Even the graph of sine, cos, and tan. You need to know all those basic graphs, right? So after sketching here, we needed to do it. After sketching from part B, we wanted to show that there is a root between 0.3 and 0.45. So we used the intermediate value theorem to take note of the sign change. Then from there, we applied the Newton-Raphson. So here, guys, you needed to be careful about the Newton-Raphson. You needed to be careful. And like what they've said, they said ask it as to find if the root is between 0.3 and 0.45. And coming back to the solution, which we have here, it's 0.446, which is in between. So guys, I'm signing out. Take care.